We know that a flow unit enters a process and leaves a process, let's say, every x units of time. In an ideal situation, we are going to expect one flow unit every x units of time. But in reality, we never achieve such a smooth flow. There are always some interruptions. One of the most important reasons why we have these interruptions is setup times. So, in this chapter, we focus on setup times and we also look at economic order quantity model. Let's look at an example of buying a custom shirt. This can be ordered online. It has many styles and it comes in many sizes, and there is a lead time of 4 weeks. If you look at the processes involved, there's a cutting department, and when one style changes to another style, obviously there will be some setup time involved. There's a sewing department and there's a process involving finishing. When we do process analysis involving batching, we can calculate capacity for a given batch by using this formula. Note that it includes setup time in the denominator. If you take this example of the cutting machine, time per unit is about 4 and setup time is 20 minutes. The relationship between batch size and capacity is shown in the graph. Now P is 4 minutes of cutting time in this example. If you calculate 1 by P, we get 0.25. So 0.25 is the limit for this capacity. Capacity cannot be more than that. If we consider examples of producing two products, in this case, one is sedan and other is station wagon, we can see that when we have large batches, we end up with higher cycle inventory compared to when we have smaller batches. So one implication of this is if the setup occurs at a non-bottleneck, we should go for decreasing the batch size, and if the setup occurs at a bottleneck, then we should increase the batch size. Let's look at one example where for the cutting machine we have been given the batch size of 15 and we want to find out what is the capacity of the overall process and also how would you set the batch size. So what is the ideal batch size given this data? So we can make use of the formula given earlier for calculating capacity for each process. So based on the capacity calculations, we see that the smallest capacity is for section 2 process. So there we have output of only 0.167 units per minute compared to other ones. So that's why this is the bottleneck. And since setup occurs at a non-bottleneck process, we decrease the batch size to match capacity at section 2. So in this example, the batch size should be set at 10. So processes that involve setup times, if setup times can be reduced, process can become quite flexible because if the setup times are high, the tendency is to go for very large batches. One of the methods for reducing setups which has become very popular is SMED, which is single minute exchange of dies. So this terminology comes from those processes that involve very heavy dies, like thousands of tons, and moving them around or changing them in press shop can sometimes take more than 6 hours. So single minute means single digit. So for example, 10 has two digits. So the idea is to achieve less than 10 minutes. And the process involves six stages. You start with stage 1, where we measure the total change over time. And in step 2, we determine internal and external activities. So internal activities are those where machine has to be stopped, and external activities are those where the machine need not be stopped. So once we find which activities are internal and which activities are external, then we move external activities to before or after the shutdown of the machine. Stage 4 involves improving the internal activities. So, improvement means if it can be done in less time, that is always helpful. And once that is achieved, then we move on to improving the external activities. And this involves finding ways to reduce this time to a smaller time. So, one example could be, let's say, if a very heavy die is placed a bit far away in terms of distance from the machine, and when the time comes to change the die, one has to bring that heavy die all the way near the machine. But if somehow the distance can be reduced, obviously it can help in reducing the overall time. And finally, the sixth stage of SMED process is to standardize procedures so that this reduced time can be consistently achieved. To summarize process analysis with batching, where we have low volume and high variety operations, we also looked at this formula for capacity when batch size is given. We can improve the process by following these guidelines for setting the batch size. Like if the setup occurs at the bottleneck, we increase the batch size, otherwise decrease it, and then we find the right batch size by solving the equation. And we can also improve the process by reducing the setup times. Next, we look at setup costs, which includes EOQ formula, quantity discounts, and converting setup times to setup costs. We will look at this example where we are ordering handle caps for scooter. 85 cents to purchase each handle cap. $300 is the fee every time an order is placed. 700 is the demand per week. And also note that handle cap is actually a pair. One is needed per scooter. Annual inventory holding cost is 40%. So the key question is, how many handle caps should they order each time they order from their supplier? Let's say we decide to time arrival of our shipments to a situation when the inventory level reaches zero. When we are ordering from an outside supplier, generally when the shipment comes, we'll have this kind of pattern where suddenly our inventory level rises from 0 to Q, and then gradually it decreases based on the demand rate. And again, when the inventory reaches 0, we order Q items. So Q divided by R gives us time between shipments. Q is the quantity that we order, R is the demand rate. Cost calculations are explained here. Purchase cost will be 85 cents per unit times 700 per week, which is the demand, and we get $595 per week. You can note that Q is not going to have any impact on the purchase cost. Now, looking at the inventory holding cost, we are given annual holding cost of 40%. You multiply that by the per unit cost, so you get cost to hold a unit for 1 year. Per week will be divided by 52. And note that because the order size is Q, average inventory is going to be half of that. So we multiply H times Q by 2, we get average inventory cost per unit time. Now, if you look at the setup cost, which is ordering cost in this case, so the fee is $300 per order, and time between orders is Q over R. So if you divide K by Q over R, we get setup cost per unit time. So when we add the setup cost and holding cost, we get the cost per unit time. So the first part is setup cost, and the second part, which is H times Q over 2, is the holding cost. And if you look at the picture, as the quantity increases, you can see the cost per week also goes up. But if you look at setup cost, where Q is in the denominator, so when Q goes up, obviously setup cost will go down. For example, if orders are placed every month, there will be 12 orders during the year. But if only one order is placed throughout the year, so obviously the setup cost or the ordering cost will be incurred only once compared to 12 times in a year. And the top curve, CQ, represents the total of the two costs. So economic order quantity is the quantity where setup cost and holding costs are equal. So in the picture, when these two lines intersect each other, that's the point corresponding to economic order quantity, and that will also give us the minimum cost per unit time. So we can arrive at the formula for EOQ by equating setup cost and holding cost, and then we can solve for Q, and that's how we arrive at the formula. So once we plug in the values, we get economic order quantity of 8015. So note that at this value in the picture, the CQ curve around this area is quite flat. So if this number is slightly more or slightly less, it is not really going to have too much impact on the cost. So if we divide CQ by R, we get what is called cost per unit. This equation is very interesting. You can see that K is in the numerator, which means that as the ordering cost increases, cost per unit also is going to increase. And same thing for H. As the holding cost increases, cost per unit is going to increase. Whereas R is in the denominator. So R is the flow rate. So this means that as the flow rate increases, cost per unit is going to come down. So another way we can interpret this is as the demand, which is captured by R, increases, then the processes that have setup and inventory holding cost, they become more and more efficient. So this also indicates that as the demand increases, we gain economies of scale. So if you look at the calculations below, when we go from a flow rate of 300 units per week to 1100 per week, the economic order quantity reaches more than 10,000 units. And you can also see that the per unit cost comes down from 11 cents per unit to 6 cents per unit. So this slide gives comparison of two companies, Costco and Walmart, like how they manage their inventories and try to be more efficient. If you look at Costco, they have a gross margin of 10.5%, which is much smaller compared to Walmart, which has 23.5. Number of stock keeping units at Walmart is 60,000 and Costco it is just 4,000. But if you look at inventory turns, Costco has 12.6 and Walmart has 8.1. So obviously, Costco has to be very, very efficient when they are restocking their shelves because they have very thin margins. So, very different approaches. Coming back to the scooter example, now suppose one of the suppliers offers a 5% discount if the order quantity is 10,000 units per order. So if we do the math, we can get an answer. In the calculations, you can see that when Q is 10,000, the total cost per week is 617.31. And even when the Q or economic order quantity is 23,000, still the total cost per week, which is 645.81, is smaller than 647.4 for the original EOQ. This means that Scooter should be willing to buy even 23,000 units to get this 5% discount because this will be profitable. Sometimes supplier gives retailers temporary discount, which is also called trade promotions, and these are typically in the range of 2 to 8%. So retailers purchase enough to satisfy demand until the next trade promotion. What happens when trade promotions are available? One retailer's buy may look like this. So they purchase when there is a promotion or discount, and then there is a lean period where they do not do any purchase, and then again you see a spike indicating some kind of discount was available when the purchase was made. Sometimes there is a tendency to rely too much on setup costs rather than setup times. So one example is given here where we have milling machine cost of about $9,000 per month. So this translates to about $59 per hour. So obviously the tendency will be to reduce the number of setups and have as many units produced with the same setup as possible. So here the calculations are done for one component set which includes a steering support and two ribs. When we calculate economic order quantity, we get 1465 as a quantity or batch size that will reduce holding and setup costs. So with this, if you calculate capacity, it equates to 0.48 units per minute. But note that capacity of assembly is only 1 by 3, which is 0.33. So assembly is the bottleneck. So if we calculate the batch size, keeping in mind assembly is the bottleneck and the milling operation has a setup time, we get a batch size of 120. We can see that the EOQ batch size is much larger than necessary, and this is going to create more inventory than what is needed. So EOQ doesn't work in this setting because the setup cost, which was $9,000 per month, that's a sunk cost. With the setup cost sunk, the objective should be to minimize inventory without constraining the process flow. And in this case, the right batch size should be 120. So let's consider three processes involving production of orange juice. So if we consider a situation when no inventory is allowed between these processes or there are no buffers, then it has substantial implications for the overall flow rate. So capacity calculations show that extraction has a capacity of 80 barrels per hour, which is the lowest, and that makes extraction a candidate for bottleneck. But please note that when the filtering process is stopped for 30 minutes, extraction cannot continue because there is no buffer allowed. So basically at filtering, we can only produce at the rate of 80 barrels per hour. And if we do the capacity calculation for filtering again, we get 71 barrels per hour as the capacity. To summarize, if no buffer is allowed, then filtering is the bottleneck process and the whole process works at the rate of 71 barrels per hour. But if buffer is allowed, then the whole process can work at the rate of 80 barrels per hour. This phenomena is also called as buffer or suffer.